Hello, my name is Gary Fielding, and I'm going to talk a little bit about my project, which is a strain gauge for load-bearing orthopedic implants for use in Vivo. Every year in the United States alone, over 700,000 load-bearing implants are placed into patients. Over 40% of those are installed on patients over 65 years old, and the average implant lifetime is considered to be less than 15 years. This becomes very important because it is very likely that a patient will need at least one corrective surgery during their lifetime. The surgery is very invasive and it is difficult to do more than one revision due to cumulative damage. Patients can end up in pain for the rest of their lives or perhaps confined to a wheelchair. There are generally three modes of failure that are associated with load-bearing implants. The first, aseptic loosening, occurs when material begins to wear, causing particulate matter to be released into the surrounding environment. This can cause surrounding tissue to die and result in implant loosening. And this has actually been kind of a big problem recently with a lot of implants that are using ultra-high molecular weight polyethylene. The second is loosening due to morphological fixation. Because most implant materials are bioinert, tissue and material interaction is very low. The result is a fibrous encapsulation of the implant by the tissue that causes implant loosening. The third, which is of particular interest, is stress shielding. This occurs because the modulus of the implant material is generally much greater than that of bone. The implant material takes the brunt of the mechanical load during walking. One important thing is for bone is that it's a dynamic system and requires mechanical stimulus to stay strong. When not appropriately stimulated, it begins to atrophy and weaken. You can see the picture to the right shows what a typical failure would look like due to weakened bone. You can see fracture at the femur and hip stem interface. Recently, there has been a lot of research that has gone into the design and material selection of implants with the goal of extending the implant's functional lifetime. There are two approaches to do this. One is based on biomechanical modeling, which is really only applicable in ideal scenarios and cannot effectively take into account the damage caused during surgery, complex tissue interaction, and the fit of the implant. The more promising pathway is to collect data from the source, people who are actually walking around with an implant. This can be made possible with the use of MEMS technologies. The idea of sensors for in vivo applications isn't new. One group has already designed a piezo-resistive doped nanocrystalline silicon thin film just for this purpose. As you can see in the picture, it's almost like a flexible circuit board that's wrapped around the base of the orthopedic implant. This particular design, however, is limited to the detection of only a catastrophic failure. There are also some concerns about biofouling or malfunction due to tissue interaction and its adherence longevity. Another group has designed a capacitive pure bending strain sensor for detecting stresses and strains of bone cement in spinal fusion applications. While this is a pretty good design, it's relatively complicated and may not be able to be attached to areas of interest for extended periods of time in the body. My design objectives are pretty straightforward. The device needs to be able to operate in conditions such as temperature and pH found in the human body. It needs to be inert to tissue interactions and should have a long lifetime. It should also be able to detect a minimum strain of 10 microns and a maximum strain of 500 microns. For my materials, I have selected a titanium substrate, which is very common for orthopedic implants, and also can handle common microfabrication temperatures that are going to be used. For the piezoelectric, I'm using zinc oxide, which can actually be made to have a higher voltage output than PZT or aluminum nitride or polysilicon piezo resistors in micro applications. And another great benefit of zinc oxide is it can actually be fabricated directly onto the metal substrate. For this application, I'm going to be using direct effect piezoelectric, which just means we're going to be measuring a voltage output that is due to a mechanical input. With piezoelectrics, the voltage output can be modeled as a function of the piezoelectric's capacitance and resistance. In an attempt to explain the voltage modeling in a little more detail, I've chosen a constitutive equation for in-plane stressor strains induced from the substrate, where S1 plus S2 is the transfer function from strain input and essentially acts as a high-pass filter, which actually becomes pretty important to reduce the noise from changes in temperature. As I mentioned before, the voltage can be modeled as a function of the resistance and capacitance of the sensor. You can see an equivalent circuit on the right-hand side of the slide. This particular model includes a voltage source Vn, which is basically just a white thermal noise with spectral density. The method of fabrication for this sensor is a fairly simple process. We start with applying a 0.7 micron spin-on glass layer as an insulator, which will prevent oxidation of the metal when we put on our zinc oxide piezoelectric element. Next, we evaporate a 0.2 micron aluminum layer to form the bottom electrode, after which we'll deposit a second spin-on glass layer that will act as an adhesion and buffer layer. Next, we can deposit our zinc oxide layer of 1 micron. This is done at 300 degrees in argon and oxygen, and then after that, a third SOG layer is deposited. The zinc oxide and SOG layers can then be patterned using an SF6 reactive ion etching process. Finally, the top electrode is evaporated on, and then another SOG layer is deposited on top of that. The sensor can be completed by removing the excess SOG. Here are my references, and I would like to thank you for listening to the presentation.